The very last lesson we will do in this course gives us the ability to see how exponential growth and decay occurs in real life settings. We've already looked at how when interest is compounded continuously, that is one way in which we use that natural number E because of the exponential growth that can take place with money. But think about in science when you have biologists who are studying how bacteria grows and how things spread, or if you're talking about things that are radioactive and you want to know how long does it take for it to decay before things are safe, or how long would it take for something to break down if it's put into a recycling bin or a compost area. There's just a lot of different reasons why we might need to calculate these. So what you will see is an exponential growth or decay function, and that would mean that we have some amount that's present initially. We're going to call it y sub 0. So that's what is present at time 0. Then under certain conditions, the amount present at any time t is modeled by this equation. So y, the amount we would have after a certain period of time, is equal to y sub 0, the initial amount, times e raised to the k times t power. Now remember, t is still the period of time. K is a constant, and depending on what it is, there is a particular value of k that will be associated with it. Sometimes we will solve for what that k is. Sometimes we will be given the value for k. So here's the first example we want to look at. We're going to see how long it would take for money in an account that accrues interest at a rate of 4.25% compounded continuously to double. Well, we already have the formula for interest that is compounded continuously. That is A equals P times E to the RT power. Now that looks just like the formula for exponential growth and decay. The only difference is instead of a y sub 0, that's our P, our beginning amount, and instead of a K, we're using R for our interest rate. Everything else will be the same. Now, what we don't have here is any particular amount of money that they've given to us. It's possible to just choose X to represent our beginning amount. When it doubles, it would be 2X. Not a problem with that, but we can make it even simpler if we say, let's say it's $1. If P is $1, how much would be the amount when it's doubled? Well, that would have to be $2. And if that's the case, I can plug in now. My R, that interest rate, is 4.25%, so that becomes 0.0425 as a decimal. And what I'm trying to find is the length of time it will take to double. So T is what I'm looking for. Now, if I look carefully at this, either I can think of it as 1 times e to some power is just e to some power. That 1 is not going to affect anything. Or I could actually divide both sides by 1. Either way, I'm going to be left with 2 on the left, and I'm going to have e to the 0.0425 t power on the right. Now, if I'm solving for t, and it's in my exponent, do you remember what I can do to get something out of the exponent position? I can take the log of each side, and since my base is e, it makes the most sense for me to take the natural log. I'm going to take the ln of each side. Now, that means I just have the natural log of 2 on the left, but what happens on the right? My natural log, the reason I'm taking this is because natural log has an understood base of e, so if it's natural log base e of e to the 0.0425 t power, remember the only thing that's going to remain is going to be that exponent, 0.0425t, because the natural log, when the base matches what follows it, the answer will be the exponent. Or I could think of it as pulling the exponent down, and then the natural log of base e of e is 1. We're almost there. All we have to do now is divide each side by 0.0425. And if you put that in your calculator, be careful that you use the ln key, not the log key, and the natural log of 2. Don't forget to close your parentheses before you divide it by 0.0425, gives us a t of 16.3 years. So if you're only earning 4.25% interest, then you would need a little over 16 years for your money to double. Another example would be decay. Suppose 800 grams of a radioactive substance are present initially, and 2.5 years later only 400 grams remain. So we need to determine the exponential equation that would model this decay. So what we have is that equation y equals y sub naught e, and that is raised to the kt power. Now if we think about the pieces of information we have, the y sub 0 stands for the amount we start with. And how much did we begin with? 800 grams. How much do we end up with? 400. That's going to be the y value. Now, do I know the k? Or am I going to need to figure out what k is? I think I better figure out what k is. I need it in order to write the exponential equation that would model this. But I do know what the t is. It ended up cutting the amount of material in half. The radioactive material was cut in half 2.5 years later. So that's k times 2.5. Now, what would be the next step? Divide each side by 800. And 400 divided by 800 would be 0.5. And that is equal to e to the 2.5 times k power. And just like the last one, if what I'm trying to solve for is in the exponent, I need to take the log of each side since it's base e. Let's take the ln of each side. And what's going to happen is the natural log of 0.5 will be equal to 2.5k. When I pull this exponent down and I multiply it times the natural log of e, the natural log of e is 1, and I'm trying to find what k is, so when I divide by 2.5, I get a k value that happens to be negative. It's negative 0.277 if I go 3 places to the right of the decimal. Now, notice I'm not finished. I just needed to find k so I could write the equation, because to write the equation, I need to know the y sub naught, I need to know the k, and then I'm going to leave the t in the equation and the y in the equation. So the equation is y equals, we started with 800 grams times e to the negative 0.277 t power. That k value of negative 0.277 applies to whatever this radioactive substance is. Now, if I've got the equation, I can figure out how much of the substance would be there after 4 years if I simply plug 4 in for t. So I would have y equals 800 e raised to the negative 0.277 times 4 power. And if I were to put all of that in my calculator and clean it up, I would come up with 264.175, and I'll round to the nearest whole number, 264 grams. And that is it.